The title of my term project is Generative Modeling Approach for Generating New Designs for Clothes. In this project, my focus is on using latent variable generative modeling approaches to be able to design new clothing material from existing designs, mostly as variations of existing designs. In this work, I have extensively used variational autoencoders. Uh, the methodology basically involves trying to generate latent variables for existing designs and then alter the generated latent variables a bit and then decode the altered version to generate designs that are variations of input designs to the model. Other than autoencoders, I also tried using Pixel CNN and ByGAN in this project, but wasn't really that successful in getting them implemented. When we look at the methodology, I started with some data set that's available open source. I made use of the Fashion MNIST dataset and another dataset called as Fashion Product dataset that was available from Kaggle.com. When it comes to the modeling approaches, as I said before, VAEs have been extensively used. I tried 4 different VAE architecture, the designs of which are shown here. I started with the very simple traditional VAEs and some other VAE design that are inspired by the variational autoencoders. The size and the design of encoder and decoder modules were varied and experiments were conducted with those variations. Uh, a quick look at the VAE architecture, starting with the traditional VAE, which is the textbook VAE all of us would have seen. It has an encoder block to generate latent variables, and those latent variables are sampled and then decoded to produce output samples. Inspired by variational autoencoders using hierarchical latent variable structure, I tried to come up with 3 new designs, which are relatively simple in comparison with the original hierarchical VAE papers. When we look at hierarchical VAE1, the variation is that you start by generating a latent variable using an encoder module and then follow them with subsequent latent variable modules where we have a latent variable model followed by a sequence of dense blocks to lead to the next latent variable model and so on. A variation of that design would be VAE hierarchical 2, where we use latent variables in a sequential format. The only difference is that the decoding uses different dense blocks than the encoding block. Uh, the hierarchical VAE3 I have here has a parallel encoding structure where we build different encoders in parallel and then we generate multiple blocks of latent variables and then concatenate them together and then decode them to generate the output sample. So the objective function or the loss functions in this training process is very similar to the traditional VAs that we would have. It has a combination of reconstruction loss, which includes the cross entropy loss of the generated output in comparison with the input, and the KL divergence loss associated with the latent variables. For hierarchical variational autoencoders, where we have multiple latent variables, we have a separate KL divergence loss, one for each latent variable module. Uh, Once the network is trained, the generation of new sample pretty much involves take a user input, generate latent variables for them, and then alter the latent variable a bit. The way we can alter them is either add some noise to it, or another variation of that would be to generate latent variables from multiple samples and then concatenate the latent variable from different samples in some way or the other. And then the altered version of latent variables are decoded to produce uh, samples that are variation of the input samples that were provided to the model. When it came to the evaluation of the samples generated or the model in particular, the visual inspection of the samples generated was the most predominant approach used to evaluate the sample quality. In order to understand the quality of the latent variables, various clustering methods were taken up to see if the latent variable can show any trends within them, and also predictive models trying to predict The metadata associated with the samples were also attempted to see if the latent variable has any good information that will help us predict those metadata associated with the training data used. Uh, the experiments performed here include trying out various model designs, as I have mentioned before. Different VAE architectures that were tried were a significant part of the experiments. The latent dimension was varied. I tried latent dimension of 10 and 20 in various experiments that I conducted. The data size was varied a bit, and traditional hyperparameter tuning, trying to adjust the learning rates and other hyperparameters involved in the training were also attempted. The table here shows some quick summary of uh, the training loss values that were obtained. A takeaway is that among the designs that were tried, the traditional VAE did well. As I ventured into the hierarchical VAE design, the reconstruction loss started going up. The sample quality wasn't as good as the one that was obtained using the traditional VAEs. But the concept of hierarchical VAs was still interesting, and it's worth it to try much more uh, newer and complicated hierarchical structure in being able to come up with better models. Uh, Experiments with latent dimension size was also conducted, and the results were very similar to each other. Over here, I have shown the comparison for uh, models that were built with latent dimension size 10 and 20 for the traditional VAEs. As you can see, they're pretty close to each other, just that latent dimension size of 10 slightly outperforms a latent dimension size of 20. Uh, I tried to increase the dataset size, even though the dataset size wasn't that big. Even with a small increase in the dataset, there wasn't much difference in the model performance. They were much close to each other. There wasn't much variation in the model performance or the sample quality by varying the learning rate as well. Over here, we can see an example of the generated output from the model that were built. Uh, the first column shows the input data that we used, and the second column shows the decoded version of the input image. As you can see, there is still a big uh, clarity issue. The output sample that was generated by the decoder from the latent variable isn't as close to the input sample, so there is still a lot of noise that needs to be overcome. So that's still one of the area that needs work. But the most interesting trend that we can see is columns 3, 4, and 5. They show noise added versions. What I mean by that is you generate the latent variables, add some noise to it, and then decode. So decode them to generate a new sample. As you can see, there are variations when we generate sample by adding noise to the latent variable. So conceptually, what we can see that is if we can generate latent variables that tells us something about the input design and add some noise and decode them, we are able to produce designs that are variations of the original design, even though there is still more noise that needs to be overcome. Uh, and then I try to understand the latent variables that are generated by doing some simple clustering and predictive modeling based on them. Uh, as you can see over here, I tried two different data sets, the fashion MNIST data set and the fashion product data set. Uh, Using the latent variables that are generated, I tried to do some simple PCAs and t-SNE feature reductions to see if they form any clusters. As you can see over here, on top, we have the PCA and t-SNE outputs for the fashion MNIST dataset. You can The point cloud is color coded by the product category. There is some clustering that is being presented over here. So we can see that the latent variable is indeed telling us some information about the product category in the way they are encoded. Down below, we have PCAs and t-SNE uh, plots for the fashion product dataset, which is much more uh, which is of much higher resolution than their fashion MNIST dataset. Even here, we can see some clustering, though there is no metadata associated with it to see if the clustering corresponds to any metadata. We can still see some point clouds that form separate clusters. Um, One other thing that was tried to evaluate the latent variable was to try to build a predictive model using them, using the latent variables to see if they can predict any metadata. On the fashion MNIST dataset, I was able to achieve an accuracy close to 75% when I'm trying to predict the product category. On the fashion product dataset, I was able to achieve an accuracy of like 62% when I'm trying to predict the fit of the clothing item. Uh, so based on the work that I've done, I was able to find that the traditional VA architecture that I used was better than the hierarchical VAs I tried. The major issue that I have thus far is the noise associated with the decoded sample. The sample quality isn't that good. And predominantly, the networks used in this approach so far are relatively smaller. Uh, I feel like a much larger size network needs to be used in order to produce samples that are of really high resolution and high quality. So that would probably be the next step in trying to take this work forward. Um, we can also try latent variables of higher dimensions and more complex prior distributions and see if they help us capture the essence of the data that's used and allow us to generate samples of much higher quality. Other than the VA methods, I also tried to do uh, a similar attempt using Pixel CNN approach and ByteGANs. The implementation with Pixel CNN was not successful. The output that was produced was very, very noisy. One of the biggest drawback of the Pixel CNN method was that the training is very, very long, and it takes much longer to generate a model from which we can generate samples. ByteGAN approach was tried. It is very similar to VA in the sense that we can generate latent variables. Uh, uh, the difference between ByteGANs and VAs is that ByteGANs use discriminated loss instead of reconstruction loss. While building ByteGANs, the major problem was the stability of the training. The training was very unstable. Um, yeah, so that's pretty much a quick summary of what I tried. Um, as a takeaway, I can say that the VAE approach to generate latent variables has shown enough science that it can be used to generate newer designs as variations of existing designs.